This video will cover section 6.2, which is an introduction to differential equations as well as growth and decay models. So a differential equation is simply an equation that involves y prime, y, and x. And you're trying to solve for y. We've already done very, very simple differential equations. So for instance, if I said dy dx equals x, solve for y. So we've done this before where we bring the dx over to the right side of the x, and then to solve for y, you would simply integrate. So then y would be equal to 1/2 x squared plus c. Okay, so that essentially is solving a differential equation. So what we're going to do now is look at differential equations that not only involve just x, but also y and x. And so the equations might not be able to get into a form like this here, where I can get y in terms of x only. So they look a little bit different. So we're going to start off with some basic differential equations, and we call these differential equations that we can actually do this with, we call it separable. And the whole meaning of separable means I can put all of my y's on one side and all of my x's on the other side, and be able to take the integral. And actually, most differential equations you can't do that with, but we're just going to look at separable differential equations first, and then later on in the unit we'll look at how we can look at equations that are not necessarily separable. Okay, so for our first example, we have this equation, dy, or y prime equals 2x over y, and you can think of that y prime as dy over dx if you want to, which I prefer to do that so you can easily see how to separate this. So separable differential equations, again, like I said, you want to put y's on one side and x on the other side. So basically we're just going to like cross multiply here. So we have y dy, if you multiply the y and the dy together, equals 2x dx. Okay? So now your whole goal, if it says to solve the differential equation, that really means to find y. Find an equation for y that no longer has a differential in it. So we're going to now take the integral, because once I have the dy on one side, all in terms of y, dx on the other side, all in terms of x, you can easily take the integral. So the integral of y with respect to y, it's just the same as x with respect to x. It's going to be 1/2 y squared. Now, I know that typically when we integrate, we add a c. So I'm going to add a c, and I'm going to call that c1. On the other side, we have the integral of 2x, which we know is x squared. And when we add c, I'm going to call that c2. So if I were to get to solve this for y, this just becomes a regular algebra equation. So what you would do is you would subtract this c1 from both sides. And so if I subtract that c1, I don't know what that constant is, but I'm subtracting from another constant, and that's just going to give me a third constant. And so that third constant, we can call that c3. I'm just going to call it c. And actually, what I typically will do is skip this step entirely. But I wanted to show you that you do get that plus c on either side, but then at the very end, it all becomes just the plus c in the end. So I just leave it as plus c on the x side. Now, if we wanted to solve for y, we would first multiply by 2, so that's going to be 2x squared. And then again, if I multiply by the c by 2, 2 times c is just another constant, so we're going to call that still plus c. Now, those 2 plus c's are different c values, but that's okay. And then finally, we would take the square root of both sides to get the square root of 2x squared plus c. Now, I want to mention something here because you notice that I didn't put the plus or minus sign here. And that's because we know that this differential equation passes equal point 1, 2. So our y value is going to be positive. So therefore, the solution to our differential equation is going to be a positive square root value if it's going to pass through the point 1, 2. So we haven't completely solved. We've solved, but without the going through the point 1, 2. So now what we're going to have to do, and I'm going to bleed into this other side here, is now we would plug in 2 for y and a 1 for x, so that we can solve for that c value. And actually, you can do that at any point. You could have done it here. if you wanted to solve for the c value and then solve for y. It does not matter. So then we have 2 equals 2 plus c, square root of 2 plus c. So that's going to be 4 equals 2 plus c, so c is equal to 2. So then my final answer then would be y equals the square root of 2x squared plus 2. Okay, so let's look at a slightly different equation. So for number 2, you have to do a little bit more work in order to separate the x's and the y's. So my first step typically with these, if we don't already have this in the form dy dx, I like to put this back in the form dy dx. So y prime, I'm just going to write it like that. So I'm going to get all my y's on one side and all my x's on the other side. So in order to do that, I'm going to first subtract 5xy. So that's 50x minus 5xy. And then I'm going to multiply by that dx piece. Oh, no, I'm not going to do that yet. Before I do that, sorry, I want to make sure that this y gets on the left side. So I'm going to factor out instead, let's do 5x. So that leaves us with 10 minus y. All right, so now this 10 minus y piece, I'm going to divide by that. So I'm going to have over here 1 over 10 minus y dy, and then 5x dx. So that is the main thing here is to separate. All right, so now all my y's on one side, all my x's on the other side. So now you can integrate both sides. All right, so 1 over 10 minus y. Y is has a degree of 1, so this is going to be natural log. So this will be natural log of absolute value of 10 minus y. However, here's where a lot of people make some mistakes. This 10 minus y, I can do this in my head. A lot of you might make some mistakes here. So if 10 minus y is your u, then du is negative dy. So when you take care of that u substitution, you're going to have to throw a negative there in the beginning. So make sure you do not forget that. And then remember, the plus c doesn't matter. I'm going to add that all at the end. And then that equals the integral of 5x would be 5 halves x squared, and then I put the plus c here. Okay. And this is actually an acceptable answer for the way this problem is phrased. You don't actually have to solve for y, isolate the y. But in a lot of questions, we do want to isolate y. So if it just simply says solve the differential equation, I'm okay with that. But if it says solve or find y, which equals f of x, if it asks that, find y, then you would have to solve for y. So what I'm going to do is I'm going to leave number 2 as is. And we're going to work with the next problem, and then we're going to come back and look at how to solve the y here. Okay? So the next piece is boxed. That means it's very, very important, something that you're going to need to memorize. All right, so in many applications, so word problems, the rate of change of a variable y, I'm going to use some color coding here to help us out. So the rate of change of the variable y. All right, so rate of change means derivative, so like y prime, is proportional to, we'll use green there, proportional to, if something's proportional to something else, it means you can multiply it by a common factor, like a scale factor. So it's proportional to the value of y itself, okay? So what you can do here is create an equation. It says if y is a function of time, then that proportionality can be written as dy over dt equals ky. So dy dt, if you go back to my color, the rate of change of the variable y, that's dy dt. And then is proportional to, the way we put proportional to in math is we put a k to show that's a constant. So typically the k will represent some constant of proportionality. And then of y is that piece there. Okay, so we have dy dt equals k times y. All right, so that's what that means in mathematical terms. If I say the rate of change of a variable y is proportional to the value of y, then we have dy dt equals ky. Now, the reason why that's important is because you'll be seeing some questions where it doesn't actually give you this equation. They will say the rate of change of something is proportionate to that value of that something. And you're going to have to know and make the connection here. All right. So what this question is asking us to do is to solve for y in terms of t. So what we have here, this is just a special type of differential equation, dy dt equals ky. And they want us to solve for y. And I'll show you the importance of this when we get down to the bottom. So just to separate this, the k value is a constant. I typically keep that over on the right side, like with my t or with my x. So I'm just going to simply divide by y. I'm not going to divide by the whole ky. So I have 1 over y dy equals k times dt. Remember, k is a constant, it's just a number. So then we can integrate both sides. Integral of 1 over y is natural log of the absolute value of y, and that equals integral of k with respect to t would be kt, and then plus c. Okay. Now, if I were to solve for y, we have the natural log that we have to fix. We would take e to the on both sides. So that's going to be, and that's going to knock out the absolute value there. That's going to be e to the kt plus c. And be careful there that plus c is now in the exponent of e. All right, so we've solved for y. However, this is typically not how you would see this. I want to show you what this is equivalent to. So this plus c here, remember your exponent rules. If I multiply like bases, you add their exponents. So I'm kind of undoing that rule here. So if I multiply by another e with an exponent of c, hopefully you see that that's the same thing as kt plus c. And then this e to the c is just yet another constant. And so if we make that a c, and this is how we notate it, that e to the c is now being multiplied. And so that constant, what we call that is a capital C. When we pull that in front of the e to the kt. Now hopefully some of you are seeing the importance of that. This is an exponential model. You may have seen things like PERT, right? It's the same exact model. All right? So why this is important is if you have this differential equation that's in the form of the rate of change is proportional to the value, then what's going to happen is you're going to have an exponential model. Okay? So if I ever say that the rate of change of typically like a population or something is proportional to the value of the population, then what you're going to have is an exponential model, and you're going to use this PERT type model, C e to the kt. Okay? So what I want to do now is go back to that example 2 and now solve for y. And since we know that we have this natural log thing, we know that we're going to have that exponential model. Okay, so the first thing that I would do is multiply both sides by that negative to clear that out. So the natural log of absolute value of 10 minus y equals negative 5 halves x squared. Again, I'm multiplying by a negative, which is still going to be plus some constant. All right, at this point, I can take e to the on both sides, so 10 minus y equals e to the negative 5 halves x squared plus c. Now, we've already talked about when I have that plus c in the exponent of e, that can become a constant in front. So when I solve for y, the whole thing will become 10 minus capital C in front of e to the negative 5 halves x squared. Okay? So since we're talking about exponential equations now, we're now going to go and talk about applications with exponential growth and decay. So you've already seen this in your previous math classes. So this model here of CE to the KT or PERT, where y represents, typically we're going to be talking about populations. So y is the population after a certain time t, or if you're talking about like interest, that's the amount of interest you've earned, or the total amount after earning interest. C here is the initial value. Okay, so if you have an initial starting population, and then K is, we already talked about, is the constant of proportionality. And then obviously T is going to be time. All right, and just kind of a reminder, exponential growth is going to occur when that constant is greater than 0, and exponential decay is going to occur when that constant is less than 0. All right, so actually 1 and 2 are not really calculus problems. It's a review of stuff that, I don't know, maybe you learned in Algebra 2, possibly. So what I'm going to do is I'm going to do number 1 with you, and then I want you to do 2 by yourself. So let's do number 1. All right, so these are not calculus problems, as I said, but what we're going to do later on is involve the calculus together, and we can combine it with the old algebra 2 stuff with growth and decay, and also using calculus with it. All right, so suppose that 10 grams of the plutonium isotope were released in the Chernobyl nuclear accident. How long will it take for the 10 grams to decay into 1 gram? And then they give you the half-life of that plutonium isotope is 24,360 years. Okay, so what you have to do here, and I put here, this will usually be a two-step process. You're going to have to use the information given to solve for your constant, and then make a projection using your model. All right, so we know that 10 grams was released. We want to know when it decays to 1 gram. We're not going to use that information yet. Our first information that we're going to use is this half-life. So that means if I start off with 10 grams, it takes 24,360 years to get down to 5 grams. Okay. The way that I typically will use half-life is, so if I have y equals c e to the kt, the y is my ending population. Okay. So if I end with, I like to keep my numbers simple. If I do half-life, I'll end with 2. So that means that my starting population would have to be 1. All right. So you can do that. And then e to the k, I don't know that. And so how many years would it take for, oh, I did that incorrectly. I'm sorry. Hold on. Those should have been switched. My bad. Okay. So we start off with 2, and then we go to half as 1. So how many years does it take to go from 2 to 1? With this plutonium isotope, it would be the 24,360 years. Okay, so that's how you use the half-life. Or you could have gone straight into this formula, which is half equals this formula here. Okay, so let's just have a recap of how to solve this type of equation. So we have e, so we want to use natural log to undo that. So we have natural log of 1/2 equals 24,360k, and then divide by that 24,000. Okay, if this is not a calculator question, we would leave it like that. But typically these will be calculator questions, so if we put that into our calculator, we would get a k value of negative 1, 2, 3, 4 zeros, 2, 8. So that's our k value. Now the good thing is with an AP calculus task, you could define k once and then use k continuing on, and it would be acceptable. You don't have to put that number every single time you write that k, since you've already defined it. Okay, so that's part of our problem. So that's the first step. Now the second step is we still want to answer the question, how long will it take for those 10 grams to decay into 1 gram? So we go back to our equation, y equals c e to the kt, and we want 1 gram at the end, starting with 10 grams. And we found our k value to be that negative 0.282. And like I said, I could have just used k there, but just for the sake of the notes, I wanted you to see that. So now to solve for that, we divide by 10. And if you're all okay with me, I'm going to do all these steps in one. So when I divide by 10, you're going to have to take the natural log of that, and then you would divide by that negative 0.00028, and that would equal my 2. Okay. So if you're not good with that, then you can write out the steps for yourself, and then when you plug that into the calculator, you get approximately 80,922 years for those grams to become down to 1 gram. Okay. All right. So what I want you to do now is I want you to try doing that same thing with example 2 on your own. And so pause the video. When you unpause it, I'll have the whole problem worked out for you. Okay. So we started out with, we know this information. We start at 760 millimeters of mercury at sea level, so that's my initial value. And we know this point here. So we know at 672.71 millimeters, we have an altitude of 1,000. So the altitude is the x value, which is going to be like the t. And so that's the hardest part with this problem, is we're not dealing with like time, like a typical problem. So the hardest part is trying to figure out where all those numbers go. All right, so there's my K value. So again, pause, and let's find the pressure at an altitude of 3,000. Okay, so our final answer is 527.056 millimeters of mercury. Okay, so this is just kind of an intro again to differential equations as well as growth and decay. So in the next notes, we're going to get a little bit more involved.